Okay, so we'll just have a look at the manual of GLMNet. So this is the function that does k-fold cross-validation for GLMNet. You should understand GLMNet as lasso. And so you see, so what's interesting is you see that you have different inputs. So you have X, so this is what your regressors. You have Y, your predictors. And then you have a bunch of optional arguments. So when you have like something equal to something, then it's optional, and this is just the default. Okay? And in particular, one which is important is the number of folds. So you remember you have this cross-validation. First you divide the data in different folds, and then you use that. And we said, in the question, I tell you I want 5-fold cross-validation. So the default here is 10, but we will have to change this to 5. What you can also see is the type of arguments you need. You need X and Y to be matrices. In particular, X has to be a matrix, Y will be a vector, sorry, I should say. But you will need them to have this form. So, contrarily to LM, where we enter directly a data frame, we have data is equal to something. Here we need X and Y to be in a matrix form. So first, what you are going to have to do is extract X and Y from the data frame so that they are in matrix form, and then we run them into GLMNet. So to do that, you just you can use the code that is here. So first I extract X. So to do that, I just say A's.matrix that I apply to the dataset, and I ask to take the columns 2 to 4, Y2 to 4, because you see here that the regressors, they correspond to the columns 2 to 4. And for Y, I do the same, but except that I only take the first column. So here, that's why you have a 1. So that's what I've done here. And here I see my X and my Y appearing in my environment. Here. So I encourage you to type this or copy paste it, just to make sure you understand. And then I'll run GLMNet. So first my X is going to be my X that I have, but I'm just going to make sure, again, I take only the train test. So I'm going to select train index, comma, okay? So of course the first dimension is always the unit, and the second dimension is always a variable. So that's it. And that's the same for Y. Then I will also ask to have an intercept, just to make sure. It's anyway a default, but that's just for you to see that you can change it. And then the number of folds, I will say it has to be 5. So here you can also see the intercept. That it's in the other things. Anyway. So I can run that. Ah, yeah. Sorry. I forgot to say something. I forgot to run something. So if you want to use GLMNet, apologies, you first need, of course, to install the package and to load it. So to install the package, in case you've never done it, you can just do install dot packages GLMNet. Okay, and then it's gonna install the package GLMNet. And once you have done this, to load the package, you just need to run this command, which is library GLMNet, and then everything is gonna work. this is installing the package. Normally, not sure, but on most of this computer it's installed, but sometimes it's not for very random reasons. Once it's done, you can just apply library glmnet here, and then it's just loading the package. And when it's done, when you've loaded, you can run this, and you're gonna get glmnet. And here you see that I have an object fit lasso here. So this is a fit of the lasso. So why is it a big object? Well, it's an object because essentially this is giving me the lasso for many different lambdas. And also for the lambdas selected by cross-validation in particular. Okay. So I can go back to the tutorial, and what I'm asked to do now is compare in-sample MSE. So that's a bit coming back to the question. So sometimes we call the prediction error MSE, MSPE, there are different ways. For both OLS and the lasso, and what do we observe? Can we explain the result? Okay, so we need to compute on the train test the mean square prediction error. Should have put that MSPE on the train test for both OLS and the lasso. So how do we do that? You can have a look at the code that is here. First, we generate a function that we call MSE. And this function, what it's doing is just, I take a vector y hat, so that's a vector of prediction. A vector y, that's a vector of true value. And I just take the mean of y minus y hat to the square. That is just computing the mean square prediction error. Again, MSE and MSPE depends the type of MSE you're looking at. Now to use that, I need to compute the forecast of OLS and the forecast of lasso. And to do that, again, I can use the predict function. So this is one particular function. Just one clear thing, on the day of the exam, I will not expect you to know any function that we haven't seen in this class. But you can use the predict function. So to get the forecast of OLS, you just predict. You use predict with a fit of OLS, and then you just tell it what the data is that it has to use to do this prediction. And here, as we want in-sample MSE, so we just want the mean square error on the train set, we just give it the train set as data to do the prediction. Okay, you remember this is the data on the train index, so this is just the train set. So I can run that. Sorry, this probably disappear. And now I have my forecast of OLS, and I can have a look here. So this is my forecast of OLS. This is for the 140 observation in the train set. This is the forecast given by OLS. 10.5, 10.5, 10.4, and it goes on. Now, this is how you apply predict to the lasso. So you apply to fit lasso. In that case, you just need to give it the new value of the regressors, like the value of the regressor for which you're going to do a prediction. So here I just take my x in the train set. And when you tell it S is equal to lambda mean, that means it's using the lambda that minimizes the cross-validation criterion. So that's the best lambda according to cross-validation. So you do this. And now you see here also the forecast of the lasso. And then to compute the MSE, I just need to apply the function MSE, and I'm going to give it the forecast of OLS and the true value of y on the train set, and the forecast of lasso and the true value of y on the train set. And what do I see? The MSE of OLS on our lasso are almost the same. In that case, the low dimensional case, lasso and OLS do almost exactly the same thing. And why is this happening? Well, we can use this to check what is the lambda that is selected by cross-validation. And what you see here is the lambda that is selected by cross-validation is extremely small. So we are in a case where the criterion that the lasso solves is almost the criterion that OLS solves. You remember you had these two parts in the lasso criterion. The second part is almost zero because the lambda is almost zero. What's happening here is we are in a low dimensional setting. So in a one way OLS is optimal, the best thing you can do. And the cross-validation is realizing this. It's trying many different lambdas, and it's realizing that the lambda being very small, meaning OLS, essentially OLS, is the best thing you can do in that setting. So it's just selecting a very small lambda, and that's why in that case, lasso and OLS are almost the same. But that's because it's a low dimensional problem at the moment. This also tells you something interesting, is that by doing lasso, you cannot really go wrong, because in the cases where OLS is optimal, then the cross-validation will just give you something which corresponds to OLS essentially. And then you have this additional question where we are trying to compare the out-of-sample MSE for both OLS and the lasso. So we are going to do the same. Sorry, I will start going a bit quicker. We are going to use the predict function, but the main difference here is that we want to do that on the train set. So to select the train set, we just need to take the original data set, and rather than having train index here, we have minus train index. So this just tells it, select anything that is not in train index. And we do that both for lasso and for OLS. We obtain new forecast, and then we can use the MSE function, and we compare from y of minus train index, so that is a test set. And what do we get? We get, and that's very logical, an MSE on the test set, which is almost the same for lasso and OLS. But we already said that the lambda that is selected is very small, so lasso and OLS are almost the same, and that's logical. Okay, and then we see that they have the same MSE on both the train and the test set. And now we can inspect the coefficient of OLS and of the lasso. So that's the question E. So I'm not going to run it yet. What do you expect to happen if I look at the coefficient of OLS and lasso in this setting? Will they be close to each other or very far away from each other? They will be close to each other because we saw that the penalty parameter is very small, so OLS and lasso are almost the same, and that's what you can see here. So these are like the OLS coefficient, and these are the lasso coefficient. When you have a dot, it's an exact 0, but you see that it's almost the same, essentially, the coefficients of lasso and of OLS. Okay, so up to now we are in the standard setting. Now we are going to move to a more general setting where we have a high dimensional data set. I'm sorry, I'm going to have to go quickly on this, but so this time we want to add some predictors, right? Because we might think, I just use a simple linear model, but maybe I will do better prediction by adding interactions of my regressors, by adding the square of my regressors, using more nonlinear information. So we are going to do the same prediction exercise, except that this time the predictors will be first the three original variables and interaction of the number of rooms and the construction year and the square meters and the construction year. Then on top of that, we will take the square of all these variables, so the three original variables and of the interactions. We will also take the cube. So I'm interacting the variable and I'm putting many nonlinear terms in my regression. And even the power 4. Okay, so the idea is to say we are going to try to improve the prediction by considering a more flexible model. And again, we are going to use the first 70% drone observation as a test set. So we can use essentially the same. Then we generate, so first we will generate this interaction on power of variables and look at what is the total number of predictors. So let's do that. This is here in the code. So I will keep train index to be the same as before. But this is what I'm gonna, that's what I'm gonna do to generate my new regressors. First thing I do is I redefine my x in a way, and I take my original x, but also I take these two interactions. That's the one we had. So this is the interaction of the number of rooms and the year where it was built, and this is the interaction of the number of the number of square meters and the year where it was built. So that's the first thing I do. And then we say we are going to take the square of this, the original x on this interaction. So I take the square, then I take the cube, and then I take the power 4. And then I put all of that in a new big predictor matrix. Okay? That's what I do here. So I'm going to run this code. And I'm gonna and I'm gonna run this. And here I see that now I have 20 predictors. So I have many more predictors and somewhat dimensional. And what I'm asked to do here is to first fit OLS on the train set using LM, and then fit lasso on the train test. So you remember to fit OLS, we need to have a data, like we use LM, and we need to have a data frame. So to do that, we are going to generate a new data frame with a new predictors. So I just call it data with interaction, and I just take the data frame function and I just bind my y plus my new x that I generated here. And I'm going to get this new data frame. So you can just do that. And here, if you have a look at it, that's the new data frame, and I have many variables. Yes? You mean this one? Because we do it again because I want to have a new matrix X where I put the cube, the power 3 and the power 4. If I don't do that, then my matrix X at the moment is just this. So it doesn't have the cube, it doesn't have the square, it doesn't have the power 4.
But it does not override.
Sorry? No, it doesn't override them because it takes the original, it takes the last, so the last instance of X here at this point is this. So that includes the interaction terms. So the interaction term here, they will come here. And on top of that, I will have the square of all the things which are here, so including the interaction term, the power 3, the power 4, and so on. If you want to check, you can also just redo it, but you have to regenerate X from the beginning. You run this, you will see what X looks like. Then you run this, you will see the square appears, and then you just concatenate at the end. Okay? So what I can see in my dataset I generated is that now my outcome variable is going to be called V1, and then the rest are going to be regressors, so that the first variable. So I just need to use LM. I use this new dataset with the train index, and my formula is just V1 dot. So I want to regress V1, which is the new name, as I said, of Y, on all the rest. Then I'm going to do the same, but for lasso. So I redo exactly the same as before. I just use the new X now. And sometimes you get some warning messages, you can just ignore them. It's just like some kind of, that means there is one lambda where something weird happened, but that's fine. Yes?
Sorry, why is that dependent variable on P1?
It's just because when you do, it's a bit of a weird thing, but here we used y, where y is just a matrix, and in the way we kind of generated this matrix, weirdly, like the name of it got lost. So when you don't have a name for a variable, then it just gives it a v name. So here this is the first variable it gets, so it gets it v1, and also variables sometimes are v2, v3, v6. But that is just a coding, you can also rename if you want.
Yeah, okay, because for me, for instance, I mean, I ran this exactly the same.
So maybe you get something else that v1?
Yeah, I mean, I still have like a trees.
So maybe maybe it's a version of our difference. But that's why you just need to check, you can really check, like you can have a look here, and you can really see that the first variable corresponds exactly to what you had before, and it's called v1. So just make sure, always inspect your dataset when you create them, just have a look. There are many ways to do that. Okay, so now I'm going to use GLMNet, I did it, and then I'm asked to compare in sample and out of sample prediction, as before. So to compare in sample prediction, I first use the predict function to get the in sample prediction, and I use the predict function to, for both lasso and OLS. So that's exactly the same as before, but now my X is different, and then I can compare the MSEs on the train set. So what happens? This time, OLS on the train set does much better than lasso on the train test. Okay, so on the data, it does much better. On the data that it used for, let's say, estimation, it's doing much better. Now that doesn't mean it's good, right? Because this could be overfitting, as we discussed. That could be that you feed very well the data on which you were trained, but then you're going to do very badly on the test set. What is also interesting here is that also suggests that lasso and OLS are quite different, so that the lambda is much larger than before. So now I can again check the value of the lambda, and now it's almost, I think, 100 times larger than before. It's still small, but it's 100 times larger than what you had before. So that explains that lasso are different. Lasso and OLS are different. Then I'm asked to compute out of sample prediction. I do exactly the same. Again, as before, I just change the train index by minus train index so that it takes any observation that is not in the train set. And what's happening now? That's the most interesting part. What's happening is, so now this is the MSE of OLS on the test set and the MSE of lasso on the test set. And what do you see? You see that OLS does terrible compared to lasso, which does quite well. So here you really see what happened with overfitting. OLS could fit very well the train test, the train set, it fitted very well the data points, but it fitted their noise. So fitting the noise is completely useless on the test set, because these are new data with a different noise. And that's why OLS is doing extremely poorly in that case. But lasso, which avoids this overfitting problem, is doing much better. Okay, so I think this is kind of a striking example that if you have overfitting, things can get really, really wrong. Like this is much worse than OS. Yes?
Is there a general threshold for the least square prediction rate? So you define it as a good prediction and a good.
It's a bit hard because it depends also on the. So this is going to depend on several things. One thing is, of course, it depends on the scale of your outcome variable. So you always need to adjust for that first, because if your outcome variable is in the thousands, of course you're going to get more prediction error than if it's like in one. And the second one is that it depends on the difficulty of your problem. So it's a bit. So I would say. If you look at your, there is no like clicker rule, but if you look at your outcome variable, it's always around 10. So when you do a prediction error, a square prediction error of 6, on average, that looks very large compared to 10. That if your outcome variable was in the thousands, then that would be very small, actually. But here I would say this looks like like a very large prediction error. What's also interesting is also just to compare. And here you see that you have prediction error almost 60 times larger than the lasso. So then this is really bad in this case, compared to lasso. So not only is this, I think, bad in absolute term, but it's also bad, very bad relatively. And what's interesting is that then you can actually also compare the coefficient of lasso and of OLS as we did before, and you will see that they are quite different. So look, for instance, at the intercept. One time for OLS it's 6, for the lasso it's 1. Well, 1 times 10 to the power 1. So sorry, 60 or 1. This variable, there is also a huge difference. So you will see that the lasso gives you a very different set of coefficients, and what you also see is that the lasso is very sparse. You have lots of points, so points are exact zeros, so lots of the coefficients are exactly 0. Okay? So essentially what the goal of this exercise was really to show you like a striking example of overfitting. Here you really see I increase my number of variables and OLS goes completely wild, essentially, and the lasso is still very stable, still does well. So that's an example. This also gives you, I mean, helps you a little bit to know or to code like basic stuff in R, or to use these functions a little bit. So what you need, I think, to remember is really at the exam, you will. I try to judge you as much as I can on conceptual understanding. So what is the most important is that you remember the lasso and overfitting on these kind of things. You will have access to this tutorial anyway. It's a completely open book, so you can use the tutorial to improve your coding. You should just, I think what's important is that you know to do some simple data manipulation in R. So you know to create a new data set, you know how to select the train test and this kind of thing. Okay?
I just got a quick question about the results in lasso. So why are the variables that go around the place? So we get like the 3 variables that we have, and then probably like the squares or interaction terms, and
they don't matter much. But this is something that you can't know ex ante.
Oh yeah, no, I just mean that like if we had actual regression with actual variables, and why do we get like 3 variables and then like 2 lines of white space and then again 3 variables?
Okay. That's just because this one they don't have a name attached.
Okay.
That's again like because these are the variables which I created with my code. So they don't have a name. These ones are actually the square of these original ones, but it gives them the same name.
Okay.
But if you want to know to what they correspond, you just look. I mean, you can either rename them or you can look in the new data set, and you look at the order of variables. So these two are like the V5 and V6, and then these ones are just like the square of the original variables. Here the point 1 does not appear, and it goes on. Okay. So you will see that sometimes R does like some weird things. That's why you have to look at it, look at the data set, and try to make sure you understand what the result is. Is there any other question? Okay. So we will see each other again in the Colon Museum next week for the 3rd lecture. And then we are going to discuss more, or you can use lasso for causal inference, because here we have talked only about prediction, but when you do causal inference, you're interested in the causal effect, so you're interested in this B coefficient. So we are going to discuss like what happens with lasso when you want to, like what happens with estimation of the B with lasso in the next lecture. Okay? So see you and have a nice weekend.